Hello everyone. Today we are going to discuss a topic of a chemistry which is equilibrium. First we will cover chemical equilibrium, then later on we will cover a small topic of ionic equilibrium. So starting with chemical equilibrium, if such reaction is given, so for such a reaction we can write rate of forward is directly proportional to active mass of A to the power stoichiometric coefficient, then active mass of B to the power stoichiometry of B. Then rate of backward can be written as active mass of C to the power C and active mass of D to the power D. Here small a, B, C and D, they are stoichiometry of reactant and products. So at equilibrium equilibrium will be defined when rate of forward becomes equal to rate of backward. That is, rate of forward is rate of backward. So when we are writing rate of forward, this will be equal to Kf, some constant Kf for forward direction, some constant for backward, that is backward rate constant. These are rate constant, Kf and Kb, they are rate constant. So Kf into A to the power A and B to the power B. Similarly, so if we define this thing, so for this reaction we can say K equilibrium constant is active mass of, that is C, to its stoichiometry, then active mass of product D to its stoichiometry and active mass of reactant to its stoichiometry. Usually active mass, it is nothing but concentration. From the beginning we have taken concentration. Usually whatever amount of solute is added, it will give us some concentration and we can take it as active mass. But sometimes there may be a situation where this make a group or may accumulate at a place. So sometimes active mass is lesser than its actual concentration. For our syllabus, we consider dilute solutions and for them active mass can be taken as concentration of the solute. So whenever we are taking active mass as concentration of solute, this K equilibrium can be written as Kc and this K equilibrium can be written as Kp if we are expressing active mass of various components in terms of pressure. So at equilibrium reaction is not stopping, at equilibrium rate of forward becomes rate of backward. That is one thing, that is they are forming dynamic equilibrium, reaction is not stopping. Now for any reaction we can also write in another way, A of A giving B of B. We can write K equilibrium as moles of product, that is B to the power stoichiometric coefficient B and moles of A to the power stoichiometric coefficient A into, as there is concentration means moles by volume. So we can write it like this delta Ng form. We will discuss the delta Ng. If this A and B they are given in gaseous state, then for such reaction delta Ng will be stoichiometry of B minus stoichiometry of A. For same reaction, if we want to write Kp, then it can be written as Kp can be written as moles of B to the power B moles of A to the power A into total pressure divided by total moles to the power delta Ng. So Kc can be written as moles of product to the power stoichiometric coefficient divided by moles of reactant to the power stoichiometric coefficient into 1 by volume to the power delta Ng. Kp can be written as moles of product to the power stoichiometry, moles of reactant to the power stoichiometry into total pressure by total moles to the power delta Ng. This is very important. If you are able to write this, problems related to Lee-Chatterjee principle can also be solved in very easily. They can be solved by, if you are able to interpret from there that if you take volume is increasing, then what will be the impact on the equilibrium? Will it go in forward direction or in backward direction? That can be interpreted in just fraction of seconds. Okay. So now moving, between Kp and Kc there is a relation, that is Kp is Kc to the power delta Ng. This is for gaseous phase reaction or reactions in which at least one reactant is, one of the component is present in gaseous phase. So we can say at least one of the component is present in gaseous phase, then we can use this, or we can say Kp, Kc, RT to the power delta N. This is for homogeneous reactions. So we will take examples and we will try to explain all other concepts of this topic. Okay. So there is one problem which says that figure shows change in concentration of species A and B as function of time, the equilibrium constant Kc for the reaction. So for this the reaction is given, A gives to B and both are in gaseous state. So Kc can be written as B to the power 2 A, and from graph we can say B is 0.4 molar and A is 0.1 molar at equilibrium. So we can solve it, 0.16 by 0.1. So accordingly we can say it is 1.6. So our answer will be greater than 1. So answer will be A. Okay. So this reaction was starting with concentration of A, you see decreases with time, concentration of B, it is increasing at time, and at equilibrium it is becoming constant. So they are not changing, concentration of reactant and products are not changing, but it does not mean that a reaction is stopped. It is not, we can say at equilibrium concentration of B and A are not changing, but the rate of conversion of B into A and A into B, now that has become equal, that is rate of forward become rate of rate of forward has become rate of backward. So now moving to next question. If it is given 1 mole of ethyl alcohol was treated with 1 mole of pure acetic acid. So they have given pure, you have to see this thing, pure, then 1 mole of pure acetic acid, 1/3 of the change into the ester at equilibrium. So if I write ethyl alcohol, it is ETOH, and you are reacting it with ACOH, and you are forming ester, that is CH3 along with water. All of them are in liquid. So for such case they are given 1 mole, this is also 1 mole, and 1/3 of the acid changes, 1/3 of acid, that is 1 minus 1/3. So as stoichiometry is same, we can take that ethanol will also be reacting in the same manner as stoichiometry is same, that is 1/3. So this will be forming as 1/3 and this also 1/3. As all of them are in pure liquid state, all of them are in pure liquid state, so Kc will be written as ester into water by alcohol into acid. See, usually what we study that concentration or activity or active mass of pure liquid or pure solid. Please listen carefully, that active mass of pure liquid and pure solid is taken as 1 in heterogeneous reaction. This is not heterogeneous reaction. This is homogeneous liquid phase reaction in which none of the reactant is present in excess, also all are in liquid phase. If any one of them is present in gaseous phase, then we have to take concentration of pure liquid, pure solid as 1, or we can take concentration of pure solid and pure liquid as 1 only when it is present in excess. In this case none of the component is present in excess manner. So this can be solved 1/3 into 1/3, then 2/3 into 2/3. So it will come as 1/4. So option A, again option A correct. One more thing, we have discussed that Kp is Kc R to the power delta N. For such reaction in which all components are present in liquid phase, Kp is not defined. For such reaction, Kp is not defined. Kp is defined only when one of the reactant is present in gaseous phase. Okay. Now moving to the next question. The reaction gives, it has Kc this. Now they have given Kc for this thing. Now they are asking Kp for this. So Kc for this is given. So before that we will solve this one, this question. For this they are asking about Kp and Kc. So see, all of them are present in gaseous state. So this is homogeneous gaseous phase reaction. So for this we can write Kp barabar Kc R to the power delta Ng. And for such equation delta Ng, if you see, it is nothing but delta Ng is stoichiometry, summation of stoichiometry of product minus summation of stoichiometry of reactant. So if we take, so it is delta Ng will come as 1 minus 1 plus 1, that is minus 1. All are in gaseous state. Okay. We have taken stoichiometry of gaseous component only. However, in this case all of them are in gaseous state. So this can be written as Kp by Kc R to the power minus 1. Now usually we use formula in this and they have asked just opposite of it. It is one of the mistake done by students. They have asked Kc by Kp and we have calculated Kp by Kc. So this will become Kc by Kp is nothing but 1 by Rt. So option C is correct. I hope it is clear to everyone. Okay. Now moving to this problem. Here they have given ammonia and in the second part they have just reversed the reaction and also they have multiplied by 2. So for any reaction, if you multiply by any number x, if you multiply by a number x, then its equilibrium constant, that if you multiply by x, then its equilibrium constant will become k to the power x. So in this reaction, if I multiply by 2, so it's Kc. If I multiply by 2, then Kc of this reaction 2NH3 giving N2 plus 3H2, it will become Kc dash, it will become 4 to the power 2. I have multiplied the first equation. So it will become Kc dash into 16, that is Kc dash will become 16. Now what I have done, I have reversed the equation. So for this equation, Kc will be, Kc double dash, it will be 1 by 16. If you reverse a reaction, then K equilibrium that reaction will get reverted. If you multiply a number, that number will go into power. If you add two equations, then their K equilibrium constant will get multiplied. If you subtract two reactions, then their K equilibrium constant will get divided. If you multiply, then if you add them, then multiply, you have to multiply their equilibrium constant. If you subtract two equation, then you need to take, you have to divide it by the equilibrium constant of other reaction. And if you revert a reaction, then you have to take the equilibrium constant in the revert manner. So for this, Kc will become 1 by 16. First we have multiplied, so I have taken its square. Now I am reverting it, so I have to invert it. Now, but they are asking Kp. Again, Kp will be Kc into R to the power delta Ng. For such reaction, delta Ng will be stoichiometry of product, that is 2, minus stoichiometry of reactant, so it will become minus 2. So it will be Kp, Kc is 1 by 16 and Rt to the power minus 2. So it will become, and they have given some temperature, this. It is given in degree Celsius, so you need to convert into Kelvin and it will become 800 Kelvin. So now we can solve it. That it will become 1 by 16 into 1 by R, T is 800 and square. So correct answer will be C. Okay. So important relation is Kp, Kc R to the power delta Ng. While calculating delta Ng, we will take stoichiometry of only those components which are present in gaseous state. If such problem is given, they are asking Kc is given and now they are asking equilibrium constant. So it is similar problem, you can, means they have given this, Kc for this is 5. So if I write Hi half H2 half I2, so its Kc will be 1 by 5 because I have reverted the reaction. Now if I multiply by 2, H2 and I2, its Kc will be, that is 1 by 25, nu K, K dash, or you take it K dash, K double dash. So they are asking that only, that is K double dash. So K double dash will be 1 by 25, so 1 by 25 can be written as 0.04. Okay, moving to the next problem. If again, if equations are given and they are asking about the net K net for the final reaction. So see, they have given first equation this and they are asking about K3. They want you to give the relation between K3, K1 and K2. So if you want to write third equation, that is 6b plus d giving 2c. So you have to multiply first equation by 3 because in this case there are 6b and in the first equation there is only 2b. So you have to multiply by 3. If you multiply by 3, then its K equilibrium K1 will become, for this if you multiply by 3, then this equilibrium constant changes to K1 to the power 3. And in the second case, you have to multiply by 2. So what you have done, you have multiplied first equation by 3 and you have taken second equation and multiplied by 2, then you will get third equation. So for first equation, as you have multiplied by 3, its equilibrium constant will change to, it will raise to power 3, and you have added this reaction with second, so their equilibrium constant will get multiplied. So you have multiplied by 3, so it will go to the power. Here you have multiplied by 2, so 2 will go to the power. As you have added the first and second reaction, so their equilibrium constant will get multiplied, then you will get K3. So K3 is nothing but K1 cube into K2 square, that is option number B. Okay. They have asked so many questions on this topic, that is why I have taken these questions. Now this is a problem related to dissociation. First, if any reactant is given, if it is dissociating to give product, so you can assume initial moles are given as A, T barabar 0, they are given as A. Now at time barabar T equilibrium, we can write A minus A alpha. Very important. This should not be written as A minus 2A alpha. Irrespective of the stoichiometry, you have to write only A minus A alpha. Very important. This should not be written because alpha, it is itself defined per mole, dissociation of the reactant per mole of the reactant. So it will itself take into account all the aspect of stoichiometry. So in this case, if it is, let's say it is given B, initial moles are B, so it will be written as B minus B alpha. Or another example, 3A gives 2B, then if initial moles are 4 given, then we will write 4 minus 4 alpha. It should not be written as 4 minus 3 into 4 alpha, that is wrong. Irrespective of stoichiometry, we will write like this only, initial moles minus initial moles into alpha. Now if 4 alpha are dissociating, then we can write by stoichiometric relation 2 by 3 into 4 alpha for B moles. This is very important. Okay. So for any reaction, again I am taking, it is given 5A, if moles are given B, then we will take B minus B alpha. It is not required B minus 5B alpha. That is very important. In this problem, it is given at certain temperature compound Av2 dissociates according to the reaction 2Av2, 2Av plus B2. So to such problem, because initial pressure is given, it can be dealt, all of them are present in gaseous state. So initial pressure is P, we can write P minus P alpha. If initial moles are given, then you can write A minus A alpha. Here we can write P minus P alpha. Pressure of AB2, it will decrease proportional to the initial pressure. So this can also be written as P alpha, and this can be written as P alpha by 2. So Kp is nothing but partial pressure of AB and partial pressure of B2, then partial pressure of AB2, going by the original definition. If you write this, it will become P alpha into P alpha by 2 divided by P minus P alpha square. If you see, P will cancel out and you will get alpha square into alpha 2 into 1P and 1 minus alpha square. And they have given that you can ignore alpha because it is less compared to unity. So you can write Kp as alpha cube by 2 into P, and 1 minus alpha can be written as 1. Okay, this can be solved by your original definition. Now moving to the next problem. At the equilibrium of the reaction, observed molecular mass of N2O4 is 80 gram per mole. Okay, fine. So there is very important concept which gives us a formula. Alpha is D minus D N minus 1 into D. What is D? D is vapor density of reactant. Small d is vapor density of, it is nothing but vapor density of equilibrium mixture. N is moles of product obtained per mole dissociation, per mole reactant dissociation. So N are nothing but they are moles of product obtained on 1 mole of reactant dissociation. So if we apply this formula over here, vapor density of reactant is molar mass of reactant by 2. So in our case, reactant is N2O4. So if we see N2O4, the molar mass will come as 28 and 64, that is 90. So D will come as, capital D will come as 92 by 2, that is 46. And they have given us observed molar mass, it is given here at equilibrium. Observed molecular mass of N2O4 means they are talking about that observed molecular mass of this reacting mixture is N2O4. So vapor density is nothing but observed molar mass by 2. So small d is nothing but 80 by 2, that is 40. Now you can solve it. For this N is, for this case, on dissociation of 1 mole you are getting 2 moles of product. So N is 2. So if you apply, then you will get 46 minus 40 divided by 2, 2 minus 1 into 40, small d. So it is nothing but 6 by 40. 3 by 20. It is, if you want to convert into percentage, then it will come as 15%. You need to multiply to 100. Alpha will become 3 by 20 into 100. So this is very important formula. In this case, they will give observed molecular mass, and we are already knowing molar mass of the reactant. So we can calculate capital D, small d can be calculated by the given data. Okay. Moving to the next problem. Kc of the reaction is this at given time 0.1, 0.3. Okay, so there is another thing. We define a term which is known as reaction quotient. This is reaction quotient, and it has same mathematical expression as equilibrium constant. It has same mathematical expression as equilibrium constant. However, K equilibrium, it is constant, its value is constant, but for Q it is a variable. K equilibrium is constant but Q is variable. Also K equilibrium, it changes only with temperature. It changes only with temperature. That is why we are saying that it is a constant at given temperature, at given T. It is a variable. Initially Q will be 0. Initially Q will be 0. And as reaction progresses, this will become, Q will increase. And for any reaction, Q will try to reach to the equilibrium value, or we can say Q will always try to reach to the value of equilibrium constant. It always wants to reach to this value, K equilibrium constant. So K equilibrium, it is a constant value, Q is a variable, it can be calculated at any time with same expression. It is defined only at equilibrium. This is defined only at equilibrium. So Q is a reaction constant, they are having same mathematical expression. Moles of product to the power stoichiometric coefficient divided by moles of reactant to the power stoichiometric coefficient into 1 by V to the power delta Ng. If it is QC, QP, moles of product to the power stoichiometric coefficient, moles of reactant to the power stoichiometric coefficient into total pressure by total moles to the power delta Ng if it is QP. So they are having same mathematical expression, but this can be calculated at any time and it is a variable. However, this is constant and it can be calculated only at or defined only at equilibrium. So if any concentration terms are given, so first we can calculate Q, and if this Q is less than K, then we say reaction will go in forward direction. If Q is QA, then we say equilibrium is arrived or reaction has reached to the equilibrium. If Q is greater than K, then reaction will go into backward direction. So if we solve this, this will be Kc is given, that is 0.04, moles of PCl3 is 0.3, moles of Cl2 also 0.3, moles of PCl5 0.1 into 1 by V okay, they have not given the volume. So we as volume is not given, we need to assume, because for this reaction Kp, for this reaction if you see, delta N will come as 1. Okay, so 1 by V to the power delta N. If we take volume as 1 liter, so this will come as 0.9. Okay, and Kc is given as 0.04. So you see Q is coming as 0.9, Kc is 0.4. However, Q is coming as 0.04, Q is coming as 0.9, which is greater than Kc. So reaction will go into backward direction. If Q is greater than K, then it will go in backward direction. And for the given data with volume as 1 liter, if we take it as 1 liter, then Q will come as 0.9. However, Kc is given as 0.04. So this is higher. So reaction will go in backward direction. Okay, now moving to this topic which deals with usually Le-Chatelier's principle. If any reaction is given, so it is saying that 3x plus y gives x3y, and they are asking about this will be affected by temperature and pressure, pressure only, temperature, pressure and catalyst. So any reaction for which delta Ng, that is moles of product, stoichiometric coefficient of product minus reactant, it is not equal to 0. So then its Q will be moles of product 1 by V to the power delta Ng. So at equilibrium, Q is already Kc. So if you change volume, this Q will change. So again reaction will try to, as Q has changed, so it will try to get to the value of Kc. So if delta Ng is not 0, if delta Ng is not 0, then this reactions will be affected by change in volume also. And for Qp, let us say this is Qc. So for Qp, it will be moles of product to the power stoichiometric coefficient, moles of reactant to the power stoichiometric coefficient into total pressure by total moles to the power delta Ng. If you change pressure, if you increase pressure, then this will decrease, or vice versa. If you decrease pressure, then this will increase. So value of Q is changing. If it increases, then it will try to come into backward direction to become equal to Kp. If it decreases, then it will go in forward direction to match its value to the Kp. So on increasing pressure also, this Kp value will change and it will again retry to become equal to Kp. So there will be effect of pressure also. And on changing temperature, any type of reaction, reactions can be defined on the basis of that is thermodynamic nature, exothermic reaction and endothermic reaction. So exothermic reactions, for exothermic reaction delta H is less than 0. For endothermic reaction delta H is greater than 0. For endothermic reaction, these are endo, on increasing temperature K equilibrium will increase. For exothermic reaction, on increasing temperature K equilibrium will decrease. Okay. So for reaction which are exothermic, if K equilibrium decreases, then reaction will go in backward direction, that is backward, it will go in backward direction. Okay. These reaction will go in backward direction on increasing temperature, and these reaction will go in forward direction on increasing temperature. On increasing temperature. Okay. So there will be effect of temperature as well as pressure for this, because for this delta Ng is less than 0 or delta Ng is minus 2. So if we see with this concept, we can say if you increase pressure, as delta Ng is minus 2, so this will become, if you increase pressure, so pressure to the power minus 2, this part will, if you see overall, it will decrease, and so Qp will increase. If Qp is increasing, then reaction will go in backward direction. Okay, I will summarize this thing. For any reaction for which delta Ng is greater than 0 and Qc can be defined as moles of product so delta Ng is positive. So if you increase volume, this Qc will decrease. So reaction will move in forward direction. So whatever is the effect of volume, the effect of pressure will be opposite. So for reactions related to delta Ng greater than 0, you require high volume and low pressure. These equations required high volume and low pressure to move into the forward direction. Very important thing. And this can also be seen by Qp. As delta Ng is greater than 0, if you increase pressure, this Q will also increase. So if Q is increasing, that means Q will become greater than Kp. So reaction will go in backward direction. On increasing pressure, reaction will go in backward direction, but if you decrease the pressure, then reaction will go in forward direction. That is why for delta Ng greater than 0 equation, best situation for industrial processes to make them into forward direction, it is high pressure, low volume. For this reaction, PCl5 given PCl3 plus Cl2, all are in gaseous state, this reaction will move into forward direction by taking high volume and low pressure. And for most of the dissociation reaction, delta H will be greater than 0. If it is endothermic, so this can also be moved in forward direction by increasing the temperature. Another very important point, effect of inert gas, effect of addition of inert gas. Simply, if you add inert gas, then it is not going to react with reactant or product. So it will not change moles of product, there will be no change in moles of product, okay, there will be no change in moles of reactant. Effect of inert gas, that it will not react with product or reactant, so moles of product and moles of reactant will not be changing. But what it will do, if it is coming into a container, it will increase the volume or it will increase the pressure. Okay. So according to this, effect of inert gas at constant volume or at constant pressure. At constant volume, it is not able to change moles of product, moles of reactant, as well as if volume is constant, then this will also not be changing. So all things are remaining constant and Q will also not change. If Q is not changing at equilibrium, then we can say that there will be no effect of addition of inert gas at constant volume. Very important point. There will be no effect of addition of inert gas at constant volume because it is not affecting moles of reactant, moles of product, also it is not able to affect the volume. You can also check this by this expression. At constant volume, total pressure by total moles will be constant. This ratio will be constant. So as this is constant, this is also constant, this is another constant, again Q is not changing. If there is no change in Q, Q is equal to equilibrium constant, so there will be no effect. So at constant volume, there will be no effect of addition of inert gas. But at constant pressure, this NP is not changing, this moles of product are not changing, moles of reactant are not changing, this total moles are changing, but pressure is constant, so this is also not changing. As total moles are increasing, delta Ng, if delta Ng is positive, so 1 by Nt will decrease, so Q will also decrease. For delta Ng, this is I am writing for delta Ng greater than 0. If Q is decreasing, then reaction will go in forward direction. So to summarize, for delta Ng greater than 0 type of reactions, best condition to move in forward direction is high volume, low pressure along with addition of inert gas. Addition of inert gas at constant pressure. So if I summarize this part, this problem we will do later. For delta Ng greater than 0, the best situation is high pressure, low volume and addition of inert gas at constant pressure. At constant volume, there will be no effect of addition of inert gas for any type of reaction, even it is delta Ng 0, not 0, greater than 0, less than 0. If we know for delta Ng greater than 0, then we can also say for delta Ng less than 0. It will be low pressure, high volume. And addition of inert gas, it will make reaction into backward direction. For delta Ng greater than 0, for delta Ng barabar 0, no effect of volume, pressure or addition of inert gas. Inert gas. Addition of inert gas at constant pressure, in this case, if we take for this, it will bring into backward direction. So this is the summary for Lee-Chatelier principle. Also, if you add reactant, okay, adding reactant will make the reaction to go in forward direction only if it is present in the equilibrium part. If it is pure solid, pure liquid, in heterogeneous reaction, it will not be part of the K equilibrium, Q equilibrium. So on adding solid or liquid, if it is not part of the equilibrium expression, then it will not bring any change. So if you are adding reactant and it is part of the equilibrium constant or equilibrium expression, then we can say it will make the reaction to go in forward direction. So on adding reactant, it make to go you in forward direction. If you are adding product, then it will go in backward direction. So again I will write this. Okay. So adding product, backward direction, adding reactant, forward direction. Removing reactant, if you remove reactant, it will go in backward direction. If you remove product, it will go in forward direction. But these reactant and product has to be part of the equilibrium reaction. Let's say, for example, if it is calcium carbonate solid giving calcium oxide solid and CO2 gas. If it is this, so for this Q will be only concentration of CO2 QC and QP will be nothing but pressure of CO2 gas. So there will be no effect of calcium carbonate addition. If you add this, there will be no effect. Calcium oxide addition, no effect, as they are solid and they are not part of the equilibrium expression. So addition of calcium carbonate or removal of calcium carbonate, addition of calcium oxide or removal of calcium oxide will make no effect over here. That is one of the important thing. Okay. So this is all about Lee-Chatterley's principle. You just need to mind this. For delta Ng greater than 0, we require high pressure, low volume condition and addition of inert gas at constant pressure. Addition of inert gas at constant volume will not affect the equilibrium. There is another problem over here which says what is the wrong about the equilibrium state. This problem. Delta G at equilibrium, yes, delta G is like delta G naught plus 2.303 RT ln log Q. Important expression. At equilibrium, it will become delta G will be 0 and Q will become K equilibrium. So this will give us delta G naught minus 2.303 RT log K equilibrium. Very important point. If a reaction is having any gaseous component, so if there is any gaseous component, then you can use K equilibrium as Kp. If there is no gaseous component, you can use directly Kc. If there is no gaseous component, then you can use Kc. And in such expression, Kp and Kc, they are not having any unit. They are defined in terms when all the components are taken in standard state. So in such case, Kp and Kc, they are having no unit. Kc is defined in molarity, so it is defined in relative molarity terms, and however Kp is defined in terms of relative bar term. So that is, they are defined in terms of standard state. So if any of the component is present in gaseous state, then K equilibrium taken over here, it will be Kp. If you take concentration, if all of the component, neither of them is in gaseous state, then we can take Kc. Okay, very important. So at equilibrium, delta G is 0, K equilibrium is 0. Also at equilibrium, entropy is maximum. Okay, and Gibbs free energy is minimum. Okay, so those points to be remembered. Okay, fine. So in this case, they are asking delta G equilibrium. So this is correct, but they are asking wrong statement. The reaction ceases at equilibrium. This is not true. Reaction keep on moving forward as well as backward direction, but with equal rate. So this is wrong. Equilibrium constant is independent of the initial concentration of the reactant. Yes, that is true. Equilibrium constant, it does not depend on the concentration term. It depends only on temperature. For a given reaction, equilibrium constant is a constant. Very important. For a given reaction, K equilibrium, it varies only with temperature. It has no effect of change in concentration, pressure, volume, also addition of catalyst. K equilibrium, that is acid dissociation constant, base dissociation constant, any type of equilibrium constant, it will not be it will not be affected by concentration of the reactant product taken, or pressure, or volume, or catalyst. Addition of catalyst also do not have any effect on the K equilibrium constant. What is K equilibrium? It is K forward by K backward. Addition of catalyst increases the forward rate constant as well as backward rate constant by the same amount, by the same factor. So if it increases K forward by 2 times, then it will also increase the K backward by 2 times. So overall this constant remains same. If it decreases K forward by 3 times, it will also decrease K backward by 3 times. So there is no effect of addition of catalyst on equilibrium constant. Or doubling the volume, decreasing the volume by twice, K equilibrium will not change. Or on changing alpha, will K equilibrium will change? No. Okay. Alpha, by changing alpha also K equilibrium will not change. Let's say for some reaction K equilibrium is C alpha square. So someone say that if I change alpha, then K equilibrium will change. No. If you changing alpha, then in such case concentration will also change at given temperature. So at given temperature K equilibrium remains constant, K equilibrium will not change, and different type of K equilibrium constants are acid dissociation constant, base dissociation constant, solubility product, and they will not change by changing the alpha, concentration, pressure, volume, or catalyst. Very important point. So K equilibrium constant, it is independent of initial concentration, pressure, volume, and catalyst taken. Catalyst has no effect on equilibrium state. Yes, if you add catalyst at equilibrium, it will have no effect. So these points are very important. Okay. Okay. So now moving to the last part, last question, that they have given something, A gives V plus S, and they have given delta H, delta S, what is the equilibrium constant? Okay. So this can be done. Delta G can be defined as delta H minus T delta S naught. So first I will erase all of this. If I take, so delta G naught will be delta H naught minus T delta S naught. For this, delta G naught is, we can calculate, this is minus 30 kilojoule. We need to mind the units. It is given in kilojoule. T 300 Kelvin, and this is also 0.1. Both, all of them are given in kilojoule. So this will become, this is minus of minus. So if you see, it will become minus 30 plus 30, all of them are, both are given in, so it will become 0. So right now we have written delta G is delta G naught plus 2.303 RT ln or log Q. So at equilibrium delta G is 0, as delta G is 0 we can write delta G naught minus 2.303 RT log K equilibrium. So at equilibrium delta G is 0 and Q becomes K equilibrium. So this is 0. As this is 0, it becomes log K equilibrium 0. So this K equilibrium has to be 1. Log 1 is 0. Log 1 is 0. That is why, that is how this will become B as 1. Is it clear to everyone? Okay. Fine. So this is about chemical equilibrium. Moving to ionic equilibrium. In ionic equilibrium, it deals with the equilibrium in which some equilibrium is established between undissociated and dissociated part. So usually we will be dealing with electrolytes like acid, base, and salts. So regarding theories of acids and base, one theory is Arrhenius theory. So this theory says compounds which generate H plus in water, they will be known as acids. Acids are those compounds which will generate H plus in water, or which will increase concentration of H plus in water. They will be known as acid. And bases, compounds which increases concentration of OH minus in water. Okay. So for pure water, which we say it is neutral. So we can say concentration of H plus is nothing but concentration of OH minus. This is very important. A pure water is said when H plus and OH minus concentration is same. So according to RE-NEET theory, acids will be defined as in which H plus concentration is increased on addition of some compound, then that compound will be called as acid. If concentration of OH minus increases in water, then we will call that substance as base. Okay, fine. Now, there is another theory which is Bronsted theory, and according to this theory, acids are those compound which donates proton, and bases are those compound which accept protons. These are proton donor and they are proton acceptor. So in Bronsted theory only we define conjugate acid and base. So for any compound HA, if we write like this, H plus and A minus, this A minus it will be known as this is providing H plus, then this A minus will be known as conjugate base. If something is there like B, it takes H plus, then this BH positive, this is base because it is accepting lone pair, and this will be known as conjugate acid. Okay, so they exist in pairs. A base will form on acceptance of H plus, it will form conjugate acid. However, acid on donation of H plus, it will form conjugate base. Okay, fine. So according to RE-NEET, compounds which increases concentration of H plus will be known as acids, and which increases concentration of OH minus into water, so they will be known as bases. RE-NEET theory, it limits to the water only. It is applicable when solvent is taken as water. Bronsted theory, it is applicable to more number of compounds. There is broader theory, that is Lewis acid, Lewis base. Lewis acid are those acids which can accept lone pair, and a pair of electron. And Lewis base, these are compound which can donate lone pair. So in this reaction, NH3 plus BF3, this NH3 can donate lone pair to BF3, and they can form an adduct, So this NH3 will be known as base, Lewis base, and this BF3 will be known as Lewis acid. This will be known as Lewis base. So these are the theory, and mostly in ionic equilibrium we will be taking water as solvent. So mostly our problem will be related to RE-NEET acid and RE-NEET bases. So for pure water, we take pure water, it self ionizes to give H3O plus. One of the molecule acts as base, another will act as acid. So it self ionizes to give this. For this, its equilibrium constant will come as H3O plus OH minus divided by H2O. As H2O is present in excess, H2O is itself, it is we have taken pure water. Okay, so it is pure water. Then in such case, we will define another constant known as Kw, which is nothing but concentration of H plus into concentration of OH minus into water. And this Kw is known as self ionization constant or ionic product of water, and at 25 degrees Celsius, it has value of 10 raised to minus 14. It is around 1.01 10 raised to minus 14, but for us it will work like this. So if we take pKw is minus log of Kw. See, Kw is another equilibrium constant. And equilibrium constant of any compound or any reaction, it will change only with temperature. So this Kw can change with temperature. For water reaction, this reaction is endothermic. So if you increase temperature, its K will also increase. So pKw is minus Kw, it will become 14. So for any pure water, if Kw is this, and also from this expression we can say concentration of H plus will be equal to concentration of OH minus. So from pKw we can say that for pure water at 25 degrees Celsius, pH is 7, also pOH is 7. Okay, so for pure water, if pure water is given, so for that pH plus pOH is pKw. Or for any aqueous solution, this is applicable. At 25 degrees Celsius, we can say pH plus pOH is 14 because value of pKw at 25 degrees Celsius is 14. So for pure water, always concentration of hydronium ion will be equal to concentration of hydroxide ion. A solution is acidic when H plus ion concentration is greater than OH minus. It is not because we are adding any substance. If you are adding any substance and overall if we see concentration of H plus greater than OH minus, then we will say it is acidic. And it is basic when concentration of OH minus is greater than H plus. And it will remain neutral irrespective of value of pH. It will remain neutral if pH is equal to pOH or concentration of H plus ion is equal to OH minus. For example, at 98 degrees Celsius, this Kw becomes 10 raised to minus 12. Then pKw will become 12. Then pH plus pOH will become 12. As concentration of H plus and OH minus is this, then pH will become 6. Can be solution is acidic or basic? At that moment also we will say solution is still neutral, because in this case also for pure water is neutral only because it is containing same number of or same concentration for H plus and OH minus ion. That is one thing. So for pure water is always neutral irrespective of pH value. The reference of pH value will keep on changing. At 25 degrees Celsius, the reference is 7. Greater than 7 will give you a basic solution. Less than 7 will give you acidic solution. At 98 degrees Celsius, if this value, we consider this value as the correct value, 10 raised to minus 12, then greater than 6 will give you basic solution and less than 6 will give you acidic solution. So on increase in temperature, your reference will change. At 25 degrees Celsius, it is 7. At 98 or 100 degrees Celsius, it will become 6. So this is regarding chemical equilibrium and regarding the basic of the theory of acid and base and this pH calculation. For pH calculation, what is pH? pH is negative log of H plus. So this H plus is total concentration of H plus present in aqueous solution. This H plus should be H plus due to added substance plus H plus furnished by the water. So this is total H plus present in the solution. Okay. So for any weak acid, like if we say what is the pH of 0.1 molar CH3COH, if its K is 5 into 10 raised to minus 5. So we can say for this acid CH3COH, so there is one more point. These Ka, Kb, they are again equilibrium constant, so they will change only with water. In NCERT they are saying that for any equilibrium constant, if it is greater than 10 raised to 3, then we say that products are highly stable as compared to reactant and reaction will go for completion. If K equilibrium, so reaction will go for completion. If K equilibrium is less than 10 raised to 3, 10 raised to minus 3, then we will say reactants are more stable than product and reaction will not go for completion, or majorly at equilibrium only reactants will be present in the equilibrium. The concentration of product will be negligible if K equilibrium value is less than 10 raised to minus 3. In this case also we can say here K value is 10 raised to minus 5 in terms of 10 raised to minus 5. So if its concentration is C, we can write C minus C alpha, this will be C alpha, C alpha. So for this Ka can be defined as H plus into acetate ion by acid, so that is C alpha into C alpha by C minus C alpha. So it will come as C alpha square by 1 minus alpha. As value is very less, we can say 1 minus alpha is 1. So we can define C alpha square. So again for weak acid we can say root Ka by C. So from here we can calculate alpha. Always check value of alpha. If it is less than 0.1, okay, or less than 10%, then this assumption is correct, that we have taken 1 minus alpha as 1. So you can take alpha as this. Now H plus will become C alpha, that is root Ka into C. So from here you can calculate value of pH. So that's it for today. Thank you so much.